Hi, this is Dr. Taft, and I am going to talk to you now about descriptive statistics. The first thing we have to talk about when we talk about descriptive statistics is what we're describing. There's really two key concepts that we have to keep in mind when we're talking about the things that we're describing with statistics. The first one is a population. Now, a population is a theoretical, sort of hypothetical thing that is connected to a random process. It's a general case that is defined by a set of shared characteristics. So it's not like the population of Wisconsin, like we would use in geography. It would be a group that's with shared characteristics, like people who root for the Packers, or people with red hair, or people from Wakanda. It is not. Well, the Wakanda one's not a good example because that would be specific people. But people who could live in Wakanda maybe would be a better description of it. So, if you look at these three examples down here, this first one's not ideal because there's a physical analog, but this next one is really good because 12 gauge nickel plated steel tubes, those are all characteristics of objects. So any object, whether it exists now or existed in the past or is just imaginary, could belong to this population. Likewise, Rhode Island red chickens, that's a specific breed, so it would be any chicken now or in the future or in the past that's descended from the original source of Rhode Island red chickens. Houses in Britain, you could kind of say that. I put that in originally because if they're from, it could be future houses or houses that have been destroyed. They don't have to be physically around anymore. But that's pretty physical, so we probably wouldn't want to go with that. So when we describe populations, we describe them by parameters. And these are not things that we can ever directly observe. A parameter is a value that describes what we expect to see given the random process that we think is describing the pattern that our population is showing. So if we wanted to look at, say, the diameter of the 12 gauge nickel plated steel tubes, we would think they would probably be normally distributed around, what is it, 1/12 of an inch? I think that's 12 gauges, with some error depending on the quality of the machining process. And so the mean would be about 12 gauge, and the error would depend on the quality of the machining. But those would be hypothetical means and standard deviations because we couldn't actually ever directly measure. We can't measure every possible real or imagined 12 gauge steel tube. So we would set that up as a conceptual model with a specific normal distribution that we could use for theory. So populations are described by parameters, which are theoretical numerical settings. The concrete things that we actually measure from are samples. And a statistician considers a sample to be a concrete group of objects or individuals that have been taken from a population. So they come from that population, they've been chosen at random, and we can make direct measurements on them. So houses on Privet Drive would be in Britain, 50 random houses from a British phone directory, 50 random houses from a British property database. Those would all be examples of samples because they're specific concrete things we can point to and say, you are in the sample. And then we can measure them. We could say, how big are they, what color are they, what is their favorite flavor of pizza, that kind of thing. For a statistician's point of view, a crucial thing is that samples should be representative of the population. So anything that's in that population should have the same chance to be in the sample. That's what we mean by being a random sample. That anyone in the population or anything in the population comes, not only a subset. So a bias sample means that there are additional characteristics that limit the sample that we are taking, and so because those are additional characteristics, that's essentially defining a new population, and so it's not exactly the same population that we were thinking we were talking about. So the Privet Drive example is not a random sample of British houses. It's only houses on Privet Drive, and they probably share a lot of characteristics that don't make them typical of all British houses. So we would not want to use them as a sample if we want to talk about the population of British houses. Likewise, houses from a telephone directory are not necessarily a representative sample of all houses in Britain, because there could be, and I'm sure there are, houses that are not that are in Britain that don't have telephones. And so we're excluding all of those. And that's probably systematic exclusion, right? Those are probably houses that are in more rural locations, and probably houses in more low income locations. And in fact, there might be houses in higher income places that have multiple phones, and so we might be more likely to pick those, and so those would be overrepresented. So we wouldn't want to use the random telephone directory. We would want to have like some kind of address-based thing where each house had one entry, every house was in there, and then we pick some of them. So that is how a sample should work. And then we can measure actual concrete representative statistics when we have the sample. So we can measure each individual, and then we can take those measurements and compute descriptive statistics that describe the whole sample. So we can descriptive statistics are computed about the observations of a sample, and then later on we can take those statistics and use them to make estimates about the parameter of the population that we drew that sample from. So that's how that first part works for descriptive statistics, what we describe.